Let's continue talking about how we determine which test to use, and then we're going to talk about some of the theoretical and statistics assumptions and how they're tested and what we're theoretically looking for. And again, I really want to stress that idea that we're looking at both the practical and the theoretical in this class. I mainly talk about the theoretical in my lecture, kind of big picture, what's going on, why are we doing it? Why then there's the practical, how you actually do it, and what are the bars or standards that we have to meet for us to be able to claim that we actually have normalized data that can be used and the interpretations can be trusted with whatever statistical technique we use. And that is generally the assumptions of any statistical test and testing those assumptions. So continuing our review of the basics of what statistic to use, again, remember that we have broad categories of theoretical statistical techniques. The first one is descriptive, and that is still a statistical technique, but all we're doing is describing data. Basically, we have a single variable, and we're simply describing it. We might be describing multiple variables. That doesn't necessarily mean we're doing inferential. Inferential is when we're actually trying to infer from our sample to a larger group, or from our sample to a new sample of a similar size. And it's important to remember that inferential test is where that p-value comes in. And again, the p-value is not necessarily a gold standard, though we often talk about setting our alpha at 0.05 as the gold standard of psychology. It's important to recognize that what an inferential test is saying is I'm inferring that what I found in this sample could be found in a larger population or a different sample, and the p-value is my level of chance that I'm wrong. The smaller the chance that I'm wrong, the more we can trust that data. But whether you can truly infer that you would find that effect again is also a methodological question. So remember that a lot of inferential statistics are not also causal. So when we say we have statistical significance, all we're saying is that we found a pattern that might be found again. We're not necessarily saying that we found through statistics alone that one variable causes changes in the other. And again, we also want to keep track of whether our outcome is a categorical or dichotomous variable, a non-parametric test, versus our outcome is a continuous variable, which the vast majority of the tests that we talk about in psychology and statistics in general are parametric tests. Because one of the easiest assumptions to look at is the normal distribution of our DV. Once again, if we are making causal inferences, the statistical relationship, that p-value, is only one of the three pillars that we have to fully support to make a causal claim. So the variables must covary. The first of Mill's canons is that statistical relationship. You have to find an effect to be able to start to argue that there's a causal relationship. But in order for you to claim a causal relationship, one, you have to show the cause preceded the effect, and that has to be done methodologically. And you must rule out all alternative explanations, and that's usually called experimental control. We need all three to be able to get a causation. The reason I keep coming back to this is that you probably more than anything else you learn in this class, when reading both news articles, popular press, media, and also scientific journals, you want to be very careful. Are they implying causation? Are they stating causation? Did they actually establish causation? Because I personally have seen a lot of articles that make a strong, subtle argument towards causation when they do not have the pillars necessary to make that claim. They have a very strong correlational argument, and there is no question that still has validity. But that doesn't mean that we actually have enough information to say that if we can control one of those predictor variables, we would always see it cause a change in our outcome variable. Just again, a review of the basics. Again, all hypothesis testing is around the idea of the null hypothesis, and that's what we're actually testing. And that generally speaking, if we actually don't find a relationship, we're claiming that the null hypothesis is true. It's only with that p-value of 0.05 or lower that we have that alternative hypothesis supported. Now again, we never say it was proven, we simply say it was supported because we actually still don't know if we're right. We just have a numerical approximate percentage of how likely it is that we're right. So remember that the true state of affairs when we're doing hypothesis testing is never truly known to us. We basically, based on our data and based on our p-value, decide whether we reject the null hypothesis or we accept the null hypothesis. So if we don't reject the null hypothesis, in other words, we accept the null hypothesis, if indeed the null hypothesis was true, there was no effect, there isn't a relationship, then we didn't make error. But if in reality there really was a relationship, but we didn't agree to it, we basically said p-value wasn't high enough, we're not confident, we're not going to make this claim, that actually is a type 2 error. That's us claiming there wasn't an effect when in reality there was. And likewise, if we reject the null hypothesis and accept or support the alternative hypothesis, if indeed the null was true, we've made what generally in science we consider the worst error, the type 1. We claim an effect that isn't actually there. And again, generally speaking, what we want to do in all of this is try to end up in that wonderful situation where the null hypothesis indeed is false and we reject it, accepting the alternative hypothesis, and end up in that far bottom right box of no error. And one of the ways that we can increase our chance of doing this is through power. And remember that power is influenced by sample size and other effects. So the first thing is power is sample size. It's probably the easiest to necessarily directly affect. The larger your sample, the more people that are in it, the smaller an effect that you can find and be fairly confident it's there. Not only that, if you find a large effect in a large sample, you can even be more certain that most likely you are indeed in the power box, the no error box. You found an effect and it was truly there. Effect size, so again, how you're actually manipulating or examining the study, how you're measuring it, the more likely your instruments will reliably find an effect, and the more likely that effect will be a large effect, the more likely you will actually find support for your hypotheses. We could adjust the type 1 error rate. We don't see this a lot in psychology, but we do see it occasionally in clinical trials, especially in drugs, where there have been multiple cases where the chances that the study was wrong, so to speak, in a clinical trial was greater than 5%. Let's say it's 7 or 8% chance that it's wrong. But what we're dealing with is a disease that kills people. And that what's being found is that there's a 92 or 93% chance that this drug is significantly saving lives. The original studies on looking at small amounts of aspirin in heart attacks actually did not hit the 0.05 level. They adjusted the type 1 error rate. They adjusted alpha and said we have enough significant correlation at this point. And even if we're wrong, it's such a small cost and such a small amount of a very safe drug to give, there's no reason for us not to start doing it and stopping people from having additional heart attacks and increasing the survival rate of current heart attacks. That was the actual clinical trial. As they actually shut that clinical trial down, again with a p-value of greater than 0.05, they started to get an enormous amount of correlational data that said they made the right choice, that there indeed is a fairly strong effect that small amounts of aspirin given immediately after a heart attack greatly increase the chance of surviving the heart attack and reduce the chance of additional heart attacks. We can also adjust whether it's a one-tailed or two-tailed hypothesis, and we talked about this a lot last semester. And again, that one-tailed hypothesis, that specific directional hypothesis, is more likely to have more power. It's more likely to find a reliable effect. And finally, the between and within subjects tests. And again, across all different statistical techniques, all things being equal, within subjects test, because you don't have to adjust for the individual differences of different people, will be a more powerful test. So if you are going to absolutely try to stack the deck in a study and you had no restrictions on your choices, you would want a very large sample size, you would want a fairly significantly and meaningfully different effect size, you would want to set the type 1 error rate as high as you can and science allows. You'd want a very well supported one-tailed directional hypothesis, and if possible, you'd want to use it within subject design. Now, not all studies are going to allow us to do those things, and some of those are very hard to do, like moving the type 1 error rate. But you do want to keep these things in mind when you design your own studies. And also, if you find a study that you're reading that seems to have some pretty broad claims or claims that don't seem necessarily as strong as the authors are suggesting, ask yourself, how much power did they have? How big was their effect size? What was their sample size? How were their hypotheses suggested? Because the reverse is also true. A small sample size with a small effect size with a very high type 1 error rate, p-value of 0.01, 0.001, two-tailed hypotheses and a between subject design When it does find a difference, there is, again, a little bit more likelihood that that might not be found again if you run the study again. Now, again, the p-value is an absolute measure of probability, but it is constrained by the study that it's done within. And this is kind of going one step above and going, if we just kept running this kind of small sample size study, would we find this effect over and over again, especially if that effect wasn't necessarily a groundbreaking effect? So I definitely want you to think about this both in terms of designing your own studies, but also interpreting research articles that you may be reading. Now, parametric tests make assumptions about the shape or parameters of a population distribution, and this is mainly focused, but not exclusively focused, on the DV. We typically focus on the variance, the skewness, and the kurtosis. And types of parametric tests include regressions, ANOVAs, etc. Each test does have different assumptions, and these assumptions must be met for valid results. Now, again, remember that the tests themselves do not automatically test for assumptions. They assume that you have met these assumptions. That's why they're called assumptions. Ideally, if you have a large enough sample set, often it's a good idea to test assumptions on actual sample data. In other words, pull some of the data out that you're not going to use for your final analysis and look for assumptions there. In most cases, especially in the social sciences, we don't have samples that large, so we often will check assumptions initially as non-p-value associated hypotheses testing, but the hypothesis is simply, do I have a normal distribution? This is typically accepted, though there is some purists and statisticians that would argue there's an issue with this as well. There's various ways to test these assumptions, and we're going to talk about those next. So common parametric statistical assumptions is first, almost all parametrics tests assume that the data is normally distributed. And that means we need to test for skewness, kurtosis, and outliers. Now, the group variance, if the DV is continuous and our IV is categorical, we need to check for homogeneity of variance. That basically, this isn't looking to see if there's differences in the means. This is asking beyond the means, are we also finding differences in the variance between our categorical IVs? Because if we are, that means there's something more going on in the data that is not being captured by what our statistical analysis is looking at. If we have continuous IVs predicting continuous DVs, we need to look at homoscedasticity. Is the continuous or linear relationship between these IVs similar at different levels? And we'll talk about that again in a few slides. If we have an independent design or between subject design, we need to make sure that theoretically and through our methodology that the observation between units are truly independent. They're not influencing each other. We need to make sure that the relationships are linear if we have continuous IVs and DVs. We also, as we hit multivariate tests, need to ask the questions of, is there normal distribution in our error? In other words, not just within our effect sizes or the differences between our various categorical groups, but we also want to examine, especially in more complex models, if we're finding differences in the residual errors. Are they randomly distributed, or do we start to see patterns? And we'll talk a little bit about how to identify that as well. And finally, the last thing we want to talk about is that we want to make sure that the measures are reliable. In other words, we want to make sure that if we have a measure of a construct, it truly is measuring a single construct. And often that will be actually tested through various techniques we'll talk, including factor analysis, but also Combrux alpha. And finally, we want to make sure that if we are missing data, we want to go through the theoretical question, is that data missing at random? So let's talk about each one of these techniques with a little bit more detail. So again, if it's a parametric test, the DV is continuous, we need to test for skewness, kurtosis, and outliers. And again, skewness is simply a bar that is set by the size of your sample. So the larger your sample is, generally the more immune it is to issues with being skewed. So generally we figure out our SES, the standard error of the skewness, and then we simply multiply it by 2, both positive and negative. And then we calculate the skewness of that particular sample and ask whether or not that skewness falls within that range, plus or minus. In other words, it should be between -2 and +2. It should not be more than -2. It should not be more than +2. If it's above +2, it's positively skewed. If it's below -2, it is negatively skewed. And again, we can test this with a simple SPSS test. For outliers, so if we find skewed data, one of the easiest solutions to that is to look for outliers, scores that exceed 3 standard deviations from the mean. So the text actually says scores that exceed 3.29. You'll also find some other numbers out there, but they all center around approximately 3 standard deviations. Just make sure that if you use one of these, you have a place to sort it from. I think 3 standard deviations works fine. And again, you can use z-scores to identify outliers, or you can simply multiply your standard deviation by 3, or 3.29, and add it and subtract it from the mean, and then ask, are there any scores above or below that range? If they are, they're outliers. And one of the easiest ways to often get rid of skewness or issues is to remove an outlier. Though you do want to make sure that that outlier is truly an outlier and it isn't a meaningful part of the population. And again, that's more of a theoretical question. For kurtosis, it's the same thing. We're actually calculating the standard error of kurtosis, which again is a function of sample size, and then again adding or subtracting or multiplying it by 2 or -2. And once again, if it's below -2, it's a platykurtic distribution, very flat. The mean doesn't have a lot of meaning here. And what I mean by that is that though there is still a mean, the scores are so spread out that there's just about as many people that are 1 standard deviation below the mean or above the mean as are actually at the mean. It's a platykurtic or plateau of data. Mesokurtic is what we want, normal distribution. And if we have above a standard error of the kurtosis of 2, we have a leptokurtic distribution. And the important thing about the problem with a leptokurtic distribution is there's not a whole lot of variance. In other words, the difference between the mean and the very highest and lowest scores is very small. And a lot of times when we're actually looking at data, we're wanting variance to be able to look for differences. If we have very leptokurtic distributions, we're not going to necessarily find a lot of difference in that variance. And again, my little mnemonic that I've always used is lepus or lepto is Greek for jump or rabbit. So leptokurtic distributions, and platykurtic, I think of platypi or platypuses, platypi, probably platypi, that are very flat and low to the ground. For homogeneity of group variance, we often just will use a Hartley's Fmax test, calculates the ratios between the largest and smallest group variance. We can also use Levene's test for this. And what we're really looking for is we're wanting to find something like this, where yes, there's great differences between our group 1, group 2, and group 3 in means, but the distributions or the variance is fairly similar. What we don't want to see is something like this. The reason for this is it doesn't necessarily mean that these 3 means are not different from each other. They're just as different as the first example. The problem here is that there's something more going on. Our manipulation, group 1, group 2, and group 3, not only changed the mean, it also changed how people responded to the actual question and how they were, well, how much variance there was in that response. And that's something that might be far more interesting, but we're not capturing it with a test that's just looking at mean differences. If we have 2 continuous variables or multiple continuous variables, we can often just look for homoscedasticity by assessing or eyeballing a scatter plot. Now, as we get into more complex models and multivariate analysis, what we're probably wanting to look at is a Bartlett's test. And the idea here again is that with homoscedasticity, what we're wanting is that if we have a linear relationship between 2 continuous variables, that we should see about the same amount of variance in the low section as the medium section as the high section of that distribution or that relationship. If we find a fan shape, very little variance at the start, moderate variance at the middle, and high variance at the top, or the reverse of that, or any other shape other than a linear one, we start to have to again realize, just like the last example where the variances between the means were different, what this tells us is both of these charts would tell us the same relationship. We would get a line of best fit or a correlation between our 2 continuous variables with the same R and the same information with both of these. One of them, that prediction, the one on the left, is fairly accurate at any level you use it. The one on the right, that prediction is very accurate if you scored low on both variables, moderately accurate if you scored in the middle on both variables, and actually not accurate at all if you scored high on both variables. Again, there's more going on in the data than what we would actually get from our test, and that's why it violates the assumption. So again, with homoscedasticity, we want to see non-fan shaped, basically linear relationships with a variance between the 2 variables doesn't really differ much from level to level as we go up and down the scales. What we don't want is heteroscedasticity, where there's a fan shape, where the variance is changing as we move up and down that predicted line of best fit. The final thing I want to talk about is assessing distributions when we're missing data. So this can be we're missing data completely from a participant, or we have a participant where we're doing a regression on two variables and we only have one of those two variables, so they're not going to be included in the analysis. What we're ideally wanting is something called data missing completely at random, or MCAR. So basically missing completely at random, MCAR. This means there is no systematic pattern of the missing data. There's nothing in the study that basically predicts whether or not someone didn't complete the study. So there's data that are missing for reasons that are not relevant to any of the variables being studied. Missing data is completely due to random and is independent of observed, and this is the important part, unobserved variables. Though assessed through correlation, it can be difficult to know for sure through statistics alone. So what this basically means is that if you're missing data, what you're hoping is that you're missing data kind of randomly. So for example, if you were measuring men and women, and that's not your variable of concern, you're not actually interested in the difference between men and women, but you did collect that demographic information. If you found that women were 3 times as likely to not participate in your study or not to provide all the data, that would not be data missing completely at random. In other words, the way we look for missing completely at random statistically is basically anything that you measured, any demographics, any information you have. If you're missing data, you're wanting to ask, am I missing data systematically from one ethnicity, one age group, some variable that you actually have observed? But recognize that if you find that there is no systematic missing data on any observed variable, missing completely at random also implies unobserved variables. And there's no real way to statistically test that because you didn't observe them. That would be done more through theory, methodology, and maybe even lit review. There are other conditions we can find ourselves in. We can find ourselves at missing at random, MAR. So missing data are related to other observed variables. However, the missing data is not a function of the variable for which the data is missing. Did not take a measure for some reason not related to the treatment or outcome. In other words, we might find some minor systematic variances here, but the variances are not directly related to any of the variables that we're actually interested in. That would be still missing at random, just not missing completely at random. And then finally, we have the one place we don't want to be, missing not at random. Data is systematically missing and is a function of the variable with the missing data. Participants fail to respond because they're not comfortable with the questions, especially if they're in a particular category, or do not take the measure for reasons related to the measure. A very good example of this was actually an exercise study that had a fair amount of people actually dropping out. And at the end, what they found was that their data was missing not at random. It was in this bad category because they actually had done a measure of motivation. And they found that basically the very motivated people stayed in the study, and those without motivation did not stay in the study. The problem with this is that it's not that their data was useless at the end, but who they could generalize it to. They basically had to admit that their findings, though significant and interesting, only worked with people that were actually highly motivated. And they did not know if it worked or not with people that weren't motivated. So again, this isn't something that can be taken with a quick test in SPSS. This is more of a question of generalizability. So you want to think about, is my data showing evidence that it might be missing at random related to my outcomes, missing not at random, in other words, related to your outcomes, missing at random, there might be some systematic issues, but I don't think they're directly related to any of the things that I'm interested in measuring. And your goal is to try to make an argument that it's missing completely at random if you are missing data. Now, one of the ways to get around this entire problem is to make a study that is methodologically unlikely to have anyone not finish the study. But honestly, sometimes the things we are interested in studying are things that might cause some people to be uncomfortable and might also be things that some people are not going to want to necessarily give us all the data on. And if you are in one of those categories, you want to think about, are there ways I can increase participation so that I'm not having to think my way through these 3 different conditions?